Today we're going to talk about chemical and physical properties as well as chemical and physical changes. Before we begin really talking about all the different properties, first of all we got to talk about, well, what are the materials that we're talking about the properties of. So to begin with, what you see here is our periodic table. Periodic table is a way of listing all of the elements that you see, all the ones that we've discovered or that we've synthesized. Alright, so to begin with, what you want to look at is the element name. Alright, notice that's circled here at the top. For B is boron, the symbol is the B, and the name is boron. And then carbon is next with a big C, then nitrogen with a big N, oxygen with a big O, fluorine with a big F, and then neon with a big N and a little e. These are all of our elements. Alright, each of these elements are composed of only one type of atom. That means if you have one carbon element, it's going to be the same, or one carbon atom, it's going to be the same, it's going to have the same properties as another atom of carbon. Alright, so what you're looking at is elements, and elements are comprised of atoms. So then what is a molecule? A molecule is when two or more atoms join together. Notice I did say atoms. Alright, those atoms can be of the same or of different elements. So if you have two carbon atoms somehow joining together, or more likely two hydrogen atoms joining together, those would be a molecule. Or if you have a water, an oxygen, and another, if you have a hydrogen, an oxygen, and another hydrogen joining together, that's going to form your water. Okay, so those are molecules. When two or more atoms join together, they're considered a molecule. So let's look at this example here. We've got diatomic molecules listed along the top. There are a total of 7 diatomic molecules in all. The way I remember them is down here, if you look at the periodic table, if you go from nitrogen to fluorine, and then from fluorine down to iodine, those form what looks like a number 7. Okay? So there is nitrogen, that's 1, oxygen, fluorine, chlorine, bromine, iodine, that makes 6. Then over here in the top left-hand corner is hydrogen. Those are the 7 diatomic molecules. So notice hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, all of them join by linking one atom to another atom, both of the same element. So di literally means 2, atom means atoms, so you've got 2 atoms of one single element. Whereas polyatomic means you have many atoms of one single element. So the examples shown here are phosphorus and sulfur. Okay? Sulfur and phosphorus, they exist as a molecule with just simply sulfur atoms joined together by bonds. Same thing for phosphorus. Phosphorus atoms joined together by bonds. But that's what makes them polyatomic, is that there are multiple atoms joined together by a bond. Okay. Next, we can look at compounds. All right, so if a molecule was 2 or more atoms, a compound is a molecule that contains at least 2 different elements, meaning it needs to have 2 different types of atoms within the compound. All compounds are molecules, but not all molecules are compounds, meaning nitrogen, N2, that's a molecule because it's 2 atoms of nitrogen joined together, but it's not a compound because it's not 2 different atoms, 2 different elements that are joined together. That's why this bottom bullet says all the diatomic molecules cannot be classified as compounds. Same thing for polyatomic molecules. They're not technically classified as compounds. Now often most people will use compound and molecule synonymous, but technically it's not correct. Alright, so let's look at some of these molecules that you see up here. The way that you write molecules is you got a molecular formula for them. So fluorine, F2. What that means is you have 2 F molecules, 2 F atoms together. Whereas methane, you have 1 carbon, and that's shown here in the middle, joined to 1, 2, 3, 4 hydrogens. Okay, and that's what gives us the subscript here of 4. Whereas carbon, there's only 1 of them, but the number 1 is always omitted. Alright, so you never actually write C1H4. It's always just written as CH4. Okay. Caffeine, that's what you see, this big molecule. I'm to ask you which one is hydrogen. Which color is hydrogen? Is it blue? Is it black? Is it the white ones? Each of these individual lines here, those are considered bonds. Okay, but then all of these like balls, those are each a different atom. And this is called a ball and stick model for a molecule or a compound. So if we count up, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of the little white balls. So which one is that? Hydrogen. Okay. What about nitrogen? There's 4. Which one do those correspond to? The blue ones. Okay. Oxygen. Those ones are a little hard to see. Those are our red ones. Okay. We have 2 balls up there that are red, and so those correspond to our oxygen. And then the ones that are black, 1, 2, 3, 4, 5, 6, 7, 8. And that's why you get a subscript of an 8 for your carbon. So notice that the number that is a subscript corresponds to the number of atoms of the element whose symbol is shown directly to the left of the subscript. All right, so those are elements, atoms, compounds, and molecules. So you kind of have to think about them before you start thinking about physical properties. If you were to think about physical properties, what would you say? What is an example of a physical property? Most people respond with, the 5 senses, things you can see, feel, touch, taste. That's exactly right. Okay. Physical properties are any properties that describe the look or feel of a substance. These include the color, the shape, the texture, the phase. Is it a solid, a liquid, or a gas? Its hardness, its density. Okay, which density, if you note, changes with phase. Gas phase is less dense than the solid phase. We'll look more at that later. And then also amount. Do you have a lot of it? Do you have not very much of it? Okay, those are all physical properties. So then what are chemical properties? How do they vary from physical properties? Chemical properties are characterized by a reaction of a substance with another or the transformation of one substance to another. So basically you can't just look at a substance and know its chemical properties. You must react it to find out. That's what chemistry is all about, is performing these reactions. So in order to figure out the chemical properties of a substance, if you can just look at it and tell what the property is, it's not a chemical property. That would be a physical property. But if you must perform a reaction on it to figure it out, it's going to be a chemical property. Example of these would be decomposition. All right, so taking one big compound and breaking it down into multiple things. All right, that's what happens with like a decomposing body. The tissues, the bones even, they're starting to decompose over time. They're starting to break down and turn into smaller compounds. Burning. Okay, when you burn wood, you are literally taking the fibers, the different parts of wood, including the water, and you're burning it. You're turning it into a gas. Different bonds are broken, different bonds are forming, you're burning it. Oxidation. Okay, that's what happens when you rust, when something rusts. So you leave a piece of metal out in the rain, it's going to rust. Neutralization. That's what happens when, say, you have an acid mixing with a base. That old volcano science experiment that you made as a kid. Basically, you're mixing baking soda and vinegar together, and you're neutralizing it. And you're also producing some byproducts. Synthesis. That's when you're synthesizing a reaction. Most of our drugs, those are small molecules most of the time. They can be synthesized in a lab. And so that's what happens is you're taking small molecules and you're synthesizing them, you're combining them together to form a different molecule. Combustion, that's what happens when you use pressure to help break something apart. Okay. All of these, if you talk about at what point or what happens when you leave metal out when it rains, that's a chemical property of rusting. Okay, so these are all properties of a molecule or of a matter or of a compound. And they basically require a reaction to figure things out. Okay? So now physical and chemical changes. A physical change involves a change, a reaction that occurs, but it's only a physical property of a substance that changes, not its chemical identity. So this is why I really want to think about before molecular formulas. All right, so if we look at this first part of figure 3.4, the top part is oxygen. You see 2 red atoms joined together. So that's diatomic oxygen. And then you have methane below that, which is you've got a carbon in the middle, the black ball, surrounded by 4 hydrogen atoms. If you take that and you combust it, break it apart, you can break apart all the different atoms, and then you rearrange them, and you form new compounds out of water and carbon dioxide. If you are breaking apart molecules, you're not doing a physical change. You're literally breaking it apart into a new substance. So it's got to be a chemical change, right? A physical change is only when you're taking something that's a physical property and changing it. Meaning, let's say you've got 5 pounds of pie. If you eat half of it, you just, let's go away from eating. You just take away half, you just decrease the amount that you had. And so that would be a physical change. Okay, or let's say you have water and you heat it and it turns into steam. That's a physical change because you have water, and if you look at the molecular structure of liquid water, it's H2O. What is the molecular structure of water that's in a gas form? It's still H2O, okay? So you didn't form a new compound, you just changed the properties of it, those physical properties, okay? So that's why we really wanted to focus on these things, where if you look at the number of atoms and how they're connected, if you change either the number of atoms or how they're connected, you have made a chemical change. All right, so it's important here to think about reactants to products. Reactants are on the left side of the arrow. Products are what is created. Reactants is what you start out with. Products are created. All right. There's also 2 other important things to consider. Okay. You can have multiple reactants and multiple products. So yes, remember how the subscript for like H2, that subscript 2 told us how many atoms of hydrogen there were? The 2, the coefficient in front of the hydrogen, tells us how many molecules of hydrogen we have. So while we have 2 hydrogen atoms in H2, we then have 2 hydrogen molecules. All right? The same goes for oxygen. We don't have anything written in front of it. So if you don't have anything written in front of it, you assume that that means there's one of them. Okay? So that means you only have 1 molecule. The 2 in front of the H2O means you have 2 water molecules. All right? So let's draw this out schematic-wise. So if you have H2, it means you have H bonded to an H. There's 2 of them, okay, 2 atoms. But then you have 2 molecules of hydrogen. So you have an H bonded to H, and you've got 2 of them. So you've got 2 hydrogen atoms now, plus oxygen. How many oxygen molecules do we have? Just 1, but there are 2 oxygen atoms, okay? Those will react to form 2 waters, okay? So if we've got water molecules, they look like this. And we'll learn more about how to draw these at a later point. Okay? There are 2 of them. So if we just look at our oxygen, how many oxygens do we have? 2 of them. 2 atoms. How many oxygen atoms do we have over here? 2 of them. How many hydrogen atoms do we have? We have 4 atoms on the left side. How many do we have on the right side? 1, 2, 3, 4. So we have the same number of atoms on both sides of the arrow, but what's important is the connectivity, the bonds between them. They changed. No longer do you have an oxygen binding to an oxygen and a hydrogen binding to a hydrogen. You have a hydrogen to an oxygen to a hydrogen. Okay. So that's what makes it a chemical change, is the fact that you've got molecules that are coming together, rearranging, and forming new compounds. The equation that you see at the bottom is the exact same. Notice if you were to count all of the individual atoms, you have to make sure that there's the same number on the left and the right. Okay, and that's something we'll get to at a later point as well, called balancing an equation. All right, but the important thing to note is that you're not just making up atoms out of thin air. That would be really hard to do. You can't just say, oh, I want water, poof, there's a hydrogen atom, poof, there's an oxygen atom, poof, there's another hydrogen atom. And so you have to make sure that you're not just creating things out of thin air, but that they all came from somewhere. And where they came from is most likely a chemical reaction. All right, so these are some general ways to identify a chemical change. If you ever notice a change in odor, a change in color, a change in composition, if light is ever emitted, or if you can no longer recover the starting material via a physical reaction, all of those are ways to identify that a chemical change has taken place. They're not always a positive indicator, but if you have any of these things happen, then generally you know a chemical change took place. All right, so for instance, with the change in odor, what's going on with the change of order is sometimes you're rearranging atoms in such a way that what's called a functional group of an atom, it starts to smell different. Okay, so the atoms, the way they're connected to each other, actually control odor. So if the odor changes, you change the structure somehow. Changing color. I know some of the prettiest reactions sometimes are oxidation reactions. And so what you could actually be doing is removing an electron or adding an electron to a sample, and the sample is actually changing form. And so you're changing the color of the sample. Okay? Changing composition, emitting light, those things are also ways to identify a chemical change. All right, so then could you ever do chemistry without a chemical change? Definitely. All right, what you see here is an example of a solid going to a liquid, going to a gas. Notice in the solid phase, the molecules are really close together. Then as they melt, they turn into a liquid, so they start to be a little further apart. Then as the liquid evaporates further, it turns into the gas phase, and now they have lots of kinetic energy, lots of motion, and there's a lot of space between them. Then when they go back the other direction, you still have the same atoms, you still have the same molecules, they're just in a different form. So can you ever do chemistry without a chemical change? Yes, definitely, happens all the time. All right, so let's further classify this matter then. We've talked about physical and chemical changes, all right, but what about classifying it further than just simply physical and chemical? Number one, we can either talk about a pure substance or a mixture. A pure substance is when you only have one substance. If you have one element, you have a pure substance. If you only have one compound, it's a pure substance, okay? So by classifying either an element or a compound as a pure substance, what you're saying is that you only have one of them existing in that sample, in that substance. Whereas a mixture, if you ever have more than one element or more than one compound present, it has to be a mixture. It's no longer pure. All right? Then we can further subclassify mixtures as either homogeneous or heterogeneous. All right, homogeneous means uniform throughout. All right, I'll give you an example. Let's say you love Dr. Pepper. All right, and there's all those different flavors they say that are in Dr. Pepper. So you take a drink, and then you wait a little bit, you take another drink. Does the first drink taste the same as the second one? It should, unless you got it from a fountain that was having problems, okay? The reason it tastes the exact same is all the different components of the pop exist as sugar is not all the way at the bottom, then you have the flavoring at the top. It's all mixed together very uniformly, okay? Whereas a heterogeneous mixture is random throughout. If you expect to take a drink out of your drink and it's different from the first drink to the last, and it's heterogeneous. I'll give you an example. I really like drinking chocolate milk, but I really like the purity kind from the store. It just tastes so much better when they mix it up compared to when I mix it up. So whenever I drink a glass of purity, I get to the bottom, the same drink at the very bottom tastes the exact same as the first sip I had. But if I made it up myself, I guarantee you there's a huge chunk of chocolate syrup just waiting for me to eat at the very bottom, okay? That's heterogeneous. It's random. It's variable throughout. That first sip might be way less chocolatey than that last sip, especially if I restirred it, okay? So heterogeneous just means it's not uniform throughout. It's random. There's lots of variation to it. A bag of chips, okay? The salt isn't on the entire, in the chip mixed together perfectly. It's mostly salty on the outside. Okay, think about a pretzel. All right, those are heterogeneous mixtures. Okay, here's kind of an example that kind of lets you think about all of them together. It gives you an example of elements of compounds, which are pure substances. All of them are composed of matter, but that doesn't mean they only have one compound, one element in them. Okay? The impure mixtures are guaranteed to have at least more than one element in them. Okay? Or more than one compound. So with heterogeneous mixtures, what you've got is sand and water, oil and water. You know how they never combine. Sand and salt. Okay, they're not going to be uniform throughout. Okay, homogeneous mixtures can be further defined as either a solution or as a suspension. Okay, the suspension is things like milk, blood, fog. Okay, you have big particles, all right, and they're all mixed in together, but they're uniform throughout even so. Whereas a solution means that you've got like one major component, so like for instance salt water, you have water, and then sodium chloride is dissolved in the solution. Okay. So the main thing to note here is with the suspension is everything's kind of suspended evenly. A solution, you normally have one thing dissolved in another. Okay. So you've got your pure substances versus your impure substances, your homogeneous versus your heterogeneous, and then your solution versus your suspension. All right. Because you do have mixtures, mixtures can literally be separated physically. If you want to take advantage of some of these different physical properties, these are kind of some examples I came up with. So for instance, coffee, that's that first picture of the little coffee cup with a heart on it. What are some of the important parts of coffee? Okay, so you got the coffee beans. In my opinion, you got to have lots of sugar and lots of chocolate and some whipped cream, and then you're good. Okay. So all of those things make it so it's quite a heterogeneous mixture, especially if you got the whipped cream kind of floating on top. But in order to get to the point where you even have what exists as coffee, so let's say you don't put coffee and creamer in it, you don't put anything else on top, nothing fancy, okay? It's a pretty uniform mixture, and the reason it's pretty uniform is when you're making your coffee, you've got a coffee filter, and you've got coffee beans that you put in on the top, okay? If you've got ground coffee at the top, you're hoping that you didn't grind it up so much that it goes through your filter, okay? So what you're doing is you're literally filtering it. Okay, via filtration, you're removing the components of the bean that are soluble in water from the rest of the components of bean, which are not soluble in water. Okay, and you're filtering them with a coffee filter from the rest of the coffee that you want to consume. Okay, that's a physical separation where you're literally using a boundary with pores to separate coffee beans from the smaller particles that dissolved in the water, basically because the beans are much bigger than the particles that were soluble. So you're literally taking advantage of size, which is a physical property, to separate the coffee from the coffee beans. Okay? Or let's say with Kool-Aid, let's say you wanted to recover all of that sugar that you dissolved in the Kool-Aid. How you could do that is by looking at the differences in boiling points. Boiling points is a physical property. So by boiling off the water, your sugar, which has a much higher boiling point than water, is going to remain in the solution. Your water is going to boil off, and your sugar is going to be at the bottom. So you can physically separate the sugar, as well as the Kool-Aid, from the rest of the water that the Kool-Aid is composed of. Or distillation. In order to make alcohol more pure, what you have to do is you have to boil off the ethanol and recollect it in a different apparatus. The reason you can do this is because water's boiling point's around 100. Different alcohols are around 60s to 70s. So by boiling off the alcohol, it starts boiling at a much lower temperature, whereas the alcohol can turn into a vapor, the water's still a liquid, so it stays behind, but all of your alcohol leaves the solution. So you can get a much purer sample on the other end. Okay? But all of these different processes, filtration, boiling points, distillation, they just take advantages of different physical properties to separate the different components of a mixture. All right, so what I want us to work on now is let's practice classifying things as either physical or chemical changes. What I want you to do is I want you to take a moment, pause this video, and fill in, write down whether you think each of the examples shown here are either a physical or a chemical change. All right, so let's look at each of them. Here are the answers. Fireworks exploding, why is that a chemical change? Why? Because you've got different light emitted. Light is a great example of a chemical change. That light is actually the reaction of the emission of the different particles as they're losing energy, basically. Okay. Squeezing oranges to make orange juice. You squeeze them. Okay. You separated the liquid from the pulp from the rest of the orange, but you did not change the molecular structure, so it has to be physical. Frying an egg. When you're frying an egg, you are literally turning that gooey, runny yolk and the rest of the egg into a more solid mass, okay? Those molecules are literally denaturing, the proteins are unfolding, and you're getting a new connectivity between the different atoms, which is what gives it its structure. So that's why it's chemical change. Pouring milk on your oatmeal. You still have milk, you still have oatmeal. It's just a physical change. Burning leaves. Anytime you see the word burning, that's an immediate flag that's a chemical change. Making salt water to gargle with. All right. Whenever you've got salt water, notice that you could still you still have salt and you still have water. Whether or not you're gargling with it, it's a different situation, okay? You're just putting it in your mouth, swirling it around. It's a different situation, but it's still salt water, okay? Cream being whipped, all right? Whenever you're whipping it, you're not actually changing the components of the cream. You still have cream, okay? The way you can tell that you haven't changed it at all is if you compare cream being whipped with frying an egg. Try and unfry an egg. Doesn't work. If you just leave an egg out, does it go back to the clear with the yellow yolk in the middle? No. But as cream being whipped, if you just leave that on the countertop, it will go back to the cream form, the liquid form. So that's why it's physical. Burning toast. I had one person say, well, I don't really burn my toast that much. That browning color, that color change, that is showing you that a chemical change is taking place. You are literally changing the structure of the bread, of all the different components of your bread. You're changing them, you're burning stuff off, gas is probably coming out of your toaster. It's a chemical change. Freezing chocolate-covered bananas. You're not changing the chocolate, you're not changing the structure of the banana. You're simply changing the temperature at which the chocolate-covered banana exists. Melting ice cream, once again, it's a physical change because you could stick your melted ice cream back into an ice cream freezer and refreeze it and it would be ice cream once again. So it's got to be a physical change. All right, give it a try. One more side of this. After kind of thinking about that last list, go ahead and pause the video once again and figure out whether each of the following is a physical or a chemical change. Glass breaking, physical change. All right, you still have glass, it's just in smaller pieces. That's one of the physical properties that we talked about, is size or amount. Hammering wood together to build a house. Whenever you put a nail into wood, you're not changing the wood, you're simply separating the different components of wood to allow for the space that nail is going to take up. So it's a physical change. A rusting bicycle. Rust, that is an oxidation reaction. It's a chemical change, okay? Anytime you see the word rust, no, it's a chemical change. Melting popcorn, butter for popcorn. Melting, that's one of the phase changes that we saw. So it's simply turning the solid butter into a liquid for consumption, okay? So anytime you see melting, that is a physical change. Separating sand from gravel, physical. Spoiling food, chemical. What's going on there is decomposition. So the food is actually decomposing and or you've got growth going on it. So you either have bacteria or something growing on it. Okay. Mixing lemonade powder into water, physical. You could separate it, so it's got to be physical. Mowing the lawn. All you're doing there is cutting the grass. It's like getting a haircut. You're not chemically changing it, like getting a perm or something, but you're physically cutting it. Corroding metal, chemical. Bleaching your hair. That's another example of a chemical change. You're actually changing the bonds that exist within your hair structure. Did any of these seem surprising to you? If it did, feel free to comment on one of the discussion posts or email as well. But just kind of think about each one of these. Think about what they're composed of. Are they mixtures? Are they homogeneous, heterogeneous? Is it an element? Is it a compound? For instance, glass, that's a compound. It's made out of silicon and a couple other different things. But is it homogeneous or heterogeneous? Okay, so just kind of things to consider. Practice classifying them and thinking about what makes something a chemical reaction or a chemical change as opposed to a physical change. So today we've talked about how matter can be classified as pure or impure substances. Pure substances can be classified as elements or compounds or molecules. Mixtures can be homogeneous or heterogeneous. Chemical and physical properties help describe a substance. Chemical reactions can be classified as chemical or physical changes, and matter can be physically separated.